Hi, I'm Milad Nasr. I'm a PhD student at the University of Massachusetts Amherst. Today I'm here to talk about my new work, which is called Adversary Instantiation. It's a work on lower bounding the privacy loss for differentially private machine learning methods. It's a work that I done in my internship at Google Brain with my co-authors, Shinyoung Abaradip, Nicholas Pepperno, and Kalini. So we all know that these days most applications are using some sort of machine learning or deep learning to do different tasks such as suggestions, text completions, or recommendations. And most of these applications are being trained on some private data like your text messages, your emails, and these could have a very important privacy risk. And it's important for us to know and measure this privacy risk. By now, we know that the many of machine learning methods that are being used are not private, and they leak many private information about the users. And we saw in the literature there are several attacks like membership inference attacks, property inference attacks, or text summarization. And these attacks show that the machine learning methods can learn and memorize very private information about the training data, and the training data are usually users' private data. So one of the kind of the gold standards in privacy is using differential privacy, and and we can apply the similar method in machine learning. So we can create a machine learning method with some differential privacy guarantees. So intuitively, if we want to have have a machine learning with differential privacy, the guarantees will tells us that if we have two data sets, D and D prime, where there are very similar data sets and they only differ in one instance, and we apply some method and some function on that data sets, the output of these methods would be very similar. Or in other words, if we have an attacker who wants to distinguish if a model was applied on D or D prime, he will have a very hard time. And differential privacy will give us an upper bound on the amount of leakage. Formally speaking, we will say that a learning algorithm is differentially private if and only if the probability that any adversary can win this game, which means that can distinguish if the model was trained on D, dataset D, or dataset D prime, for any dataset and for any differing example, is less than a given threshold. And this threshold is called epsilon in the literature. It's good. So we have this machine learning with differential privacy, but there are a lot of costs to use machine learning. And it's important for us to know that are these differentially private privacy guarantees, are they tight, or they are like very conservative? So we want to see if we train a model and we have some upper bound on differential privacy on the privacy using differential privacy. Is the reality is that the attacker can achieve very similar performance to that upper bound, or that there is a huge gap? And in this work, especially, we want to look at the lower bound. So, and our method and our approach is to do adversary instantiation, which means that we create adversaries and find those lower bounds by applying those adversaries. And why this work is important, as I said, the first kind of the motivation for this work is that to see the tightness of these differentially private privacy bounds. So we want to see if the if we show that like our lower bounds are very close to the upper bounds, which means that in reality there aren't that much improvement, and any attacker can get very good, like very similar privacy leakages as suggested by differential privacy. But if there's a huge gap, then there might be some room for improvement by like using better theory. Or and the next point is that one of the uses of this work is that we can analyze the kind of this privacy leakage under different settings. And for example, we can limit the inputs to some specific constraints, or limit the access of the adversary. And these kind of settings are not modeled in differential privacy, because differential privacy usually consider the worst case kind of setting and do the analysis in the worst case. But we can apply this like empirical studies in a like different settings. And also it's good for testing new kind of uh, potential ideas that we have, like mostly for researchers, they come up with some ideas and they want to see if the kind of, if when we apply this idea, what, what will happen to this like privacy bonds. And also it's good for kind of evaluating the correctness of the code that we are writing. Sometimes we write a code, but there's some bug in the code, and then that bug will kind of cause a lot of privacy leakages. So if we do this sort of analysis, we can get a better idea if the whole code is correct or not. Let's do this. Let's create that adversary that gives us the lower bound. So in this paper, we are going to kind of model this kind of interaction between the adversary and this model trainer as a game where we have a few entities. One is the crafter. The crafter will create two dataset D and D prime as mentioned in differential privacy, and there will be only one difference between D and D prime, which would be that like differing instance. Then we send these two datasets to the model trainer. The model trainer will train a model on one of the order prime at random, and then we have the distinguisher who wants to guess if the model was trained on D or D prime. So the objective of the crafter is to create two datasets which are very distinguishable from each other, and the distinguisher wants to maximize its kind of the accuracy and the correctness of distinguishing. And the model trainer just trains the model normally. So as I mentioned before, like in differential privacy, we usually measure the kind of the privacy leakage as a epsilon. So we want to calculate, we want to get epsilon from this sort of experiment. So to do this, we create this attacker, we create crafter and distinguisher, we train a model, and then we repeat this experiment several times, and we get some sort of a measurement from the like accuracy of the distinguisher. So we get like how many times the distinguisher guessed correctly, how many times incorrectly, and using this false positive, false negative, and we can convert it back to an epsilon. And we have a theorem that shows that that been studied in previous works that shows that if a method has a specific epsilon differential privacy, the false positive and false negative are usually lower bounded by some value, and we use these lower bounds to convert this false positive and false negative back to a epsilon, and we get a epsilon this way. So for example, if you have a specific number of true positive, a specific number of false positive, we get like that epsilon would be greater, the lower bound of epsilon would be greater than some value. So so that would be the generic approach in this work. And so we specifically focus on DPSGD because it's currently the kind of state-of-the-art approach in machine learning with differential privacy, and it's kind of the most popular approach right now. One important fact about differential privacy, DPSGD, is that the DPSGD does the analysis by assuming that each step of training are being published independently. So let's start with something simple. One of the kind of most popular currently used to show the leakages is membership inference attacks. And the membership inference attacks, we will recreate a very similar attack here where we have two datasets, D and D prime. The difference between these two datasets is only one instance. Like for example, if on MNIST dataset, we only add one like more digit, and the whole goal of membership inference attacks are to find out if some example was part of the training data or not. And the crafter here is not adversarial, just randomly pick a sample from the underlying distribution, which is very similar to how the membership inference attacks work. So in the paper, we usually model this kind of interaction and setting as a game between the adversary and the model trainer, but in this talk, I'm not going to go to kind of that. Why like membership inference attacks work in general is that the machine learning methods will behave differently when you have on its samples which are part of their training data or not. So we can use like this different behavior and this difference in the loss and find out and create this distinguisher like as a kind of a threshold. If the loss is less than something, it's D prime. If it's more than something, it's D. So if we apply this attack and we compare and on a like MNIST data set, and we compare it to a theoretical bound that we get from the DPSGD, we see that there is a huge gap between like the actual privacy and the upper bound privacy and all privacy that we're getting from this like uh, attacks. And so this, as I talked before, like in differential privacy, usually consider the worst cases. We don't care that much about the kind of the average case. So in similar setting, if you want to create the kind of a worst case scenario or a very kind of malicious case scenario, instead of adding a random sample from the underlying distribution, now the crafter would be a bit more kind of adversarial. He wants to find the hardest sample to add to the training data. The exact method is in the paper. So when we create this sample and we add it to the data set, now the idea is that the difference between loss on D and D prime data set will be much higher. So it's the distinguisher will have a much easier time distinguish it between these two data sets. And if we convert it back to repeat the experiment and convert it back to epsilon, we will see that there is we have very good improvement compared to like just doing a random sample. So it suggests that like in a worst case input example, that's like uh, the bounds are not as loose as before. So one thing, as I mentioned before, that DPSGD assumes that the adversary has access to all of the intermediate steps. So one idea is that we can look at the losses of like this, look at the behavior of the model in each different iteration, and this like this series of iteration can give us more information compared to just looking at the final step. So if we like create the distinguisher in this way, that like it will look at all of the intermediate steps, and so the loss would be however. So for example, the loss of the model for a kind of this weird example that we are adding to the data set won't change that much if it's not being trained on, but it will change like while it's being trained on. And we again converted that to epsilon. We see that we have some improvement here too, but the improvement is not kind of that much. And finally, there again, the DPSGD assumes the kind of we can change the kind of the differing example between each iteration. So instead of only kind of querying on the same malicious input, we will have kind of different malicious inputs in each iteration. And the exact method again is not paper, but the important kind of lesson here is that if we do that, we again see a good jump here again that shows that these kind of assumptions that adversary can change the dataset in each iteration, the adversary can access to the like the iterations, it's very important. And when we actually create an adversary, the lower ones are getting much closer to the actual upper bound granted by the differential privacy. And finally, like we know that the DPSGD usually doesn't care about the inputs. The type of guarantees that the DPSGD gives us are based on the gradient. So instead of adding a like example to the data set, we can add a gradient. It doesn't violate anything about DP. And specifically, we kind of create a gradient which increases the distance between 2 points in the model. So the idea here is that if if this malicious looking gradient is part of the training data, then the distance between these 2 points will be much higher compared to it's not when it's not part of training data. So then again, we apply this attack. We see that actually using gradient has a good, better effect than just using inputs, because it's kind of less noisy and you can just pick only two kind of points, and it's hard to just pinpoint only 2 points in there when you are using just inputs. And finally, again, the DPSGD assumes the worst case scenario, and the worst case scenario is that when the kind of the whole data set is malicious, the whole data set is a worst case example. And when we do that, we get very similar results to the DPSGD bounds. So it suggests that so kind of the main conclusion from this work is that first, the DPSGD bounds are tight in the worst case, the kind of the cases that they analyze, and so there aren't that much improvement that we can get kind of that. Our results also suggest that in some cases when the attack adversary is more restricted, uh, maybe we can get better bonds and with some assumptions, and we need to do a lot of kind of theory work there. That's the main kind of conclusion that we can get from this sort of a study.